Hello Year 11s. In this video I will be going through the Year 11 Combined Science AQA Physics Waves topic test. Question number 1. Figure 1 shows an incomplete electromagnetic spectrum. So you've got wave A, then microwaves, B, C, ultraviolet, D and gamma. Which position are X-rays found? X-rays would be found, let's see, in position D. So that would make radio waves A, microwaves, then its infrared is B, C is visible light, question 1.2. Which three waves can cause ionization? Tick 3 boxes. So 1 mark for all 3 answers. Gamma rays, they are not in order, so it will be ultraviolet and X-rays. Most ionizing is gamma. And the least ionizing out of these 3 is UV. Next question. 1.3. Electromagnetic waves have some practical uses. Draw one line from each type of electromagnetic wave to its use. So radio waves are used for television transmissions. Microwaves can be used for television transmissions as well. So if I write visible light are used for fiber optic communications. Gamma rays are used for medical treatments. Sun tanning is ultraviolet or UV. Next question. Question number 2. Figure 2 shows some waves traveling along a rope. Show on the diagram the wavelength of one of the waves labeled with a W. So wavelength is labeled from peak to peak. So from this peak to there, and you show it with an arrow pointing there. And the amplitude of one of the wavelengths, so amplitude should be from the middle. So if I extend that, amplitude will be from the peak to the midpoint. That's amplitude. State the type of waves traveling along the rope. On the rope, explain how you can tell this type of wave is a transverse wave. Explanation: how can you tell it's a transverse wave? Now most students lost marks because we failed to connect 2 key points here. You can say the wave is moving up and down, while the energy is moving left to right. So the wave direction is in this way. while the rope is actually moving up and down. So you could say it's moving perpendicular. There's another way of saying it. The rope moves perpendicular to the wave direction. You need to connect these 2 points, how the rope is moving or the wave is moving, to the direction of the energy. Question 2.3. The waves shown in the diagram were produced in 2 seconds. Calculate the frequency of the waves. Remember, frequency is number of waves per second. So using the diagram, you need to find the number of waves that is shown here. So if you look at the diagram, from there to there is one wave. To that point is the second wave. There is the third wave, and that's 4 waves there. So using that information, so 4 waves divided by 2 seconds is 2 waves per second, or 2 hertz. Calculate the time period of the wave. Time period is given by the equation T equals 1 over F. So if you rearrange it, frequency is 1 over the time period. Oops, actually, we just need the time period. We don't really need to rearrange it. Let me get rid of that equation. Yeah. So 1 frequency above is 2. So 1 divided by 2 is 0 0.5. 0 0.5, and the unit is, time period is second, so the unit will be seconds. Question number 3. Microwave ovens use microwave radiation to cook food. The instruction manual of a microwave oven stated that frequency of microwave is 10,000 million hertz. Now, million, this is where most of the students made mistakes. Million is 10 to the power 6. Wavelength is 0.02 meters. Calculate the speed of waves in the microwave according to the information in the instruction manual. Give your answer in standard form. So, wave speed is frequency multiplied by the wavelength. The frequency, I'm going to add that as 10,000 times 10 to the power 6, which is the million, multiplied by 0.02 using the calculator. So 10,000 6 multiplied by 0.02 gives me 1, 2, 3, 4, 5, 6, 7, 8 zeros. So in standard form, that would be 2 times 10 to the power 8. 2 times 10 to the power 8, or 200 million meters per second. Question 3.2. The speed of visible light is 3 times 10 to the power 8 meters per second. This is 300 million meters per second. Was the information in the instruction manual correct? No. The instruction in the manual was not correct. No. Explain your answer. All electromagnetic waves have the same speed of 3 times 10 to the power 8 meters per second. Next question, 3.3. Simon said, when the microwave is working, it lights up. Thus the microwaves. Explain whether Simon was correct. No. So the light that is coming from the light bulb, which is visible light. So the light is visible light from the light bulb. Microwaves cannot be seen or detected by human eyes. Next question. 3.4. Putting a beaker of water in a microwave and turning it on for a minute or two will increase the temperature of the water. Describe an experiment to investigate the relationship between the time the microwave is on and the increase in temperature of water in a beaker. Now, if you want to know the increase, you need to know the start and end temperature. So the microwave is being switched on for 1 or 2 minutes. You have to describe an experiment to investigate the relation between the time the microwave is on and the increase in temperature. Include the equipment you will use, the measurements you will take, the safety precautions. So let's say you take a beaker and you fill it with water, let's say 100 milliliter, using a measuring cylinder, and you will need a thermometer. What do you do? Let's write this down. use a measuring cylinder to add 100 milliliter of water to a beaker. Next, use a thermometer to measure the starting temperature. Then place the beaker and place the beaker in the microwave. Place the beaker in the microwave and switch on for 1 minute. Once you switch on for 1 minute, once the minute's over, you'd want to take it out and record the temperature to find the temperature difference. So remove beaker from microwave and record the end temperature of water. In brackets, I'm going to write stir well before you do that. You want the water temperature to be uniform, so stir well, but you wouldn't want to leave it for too long before you take the temperature. Then you can then repeat for a range of times, let's say 1, 2, 3, 4, 5 minutes. I'm giving this in minutes. It can be in seconds as well. Plot a graph to show the pattern. I think I missed one point. So remove beaker from microwave and record the temperature of the water. Right, I'm going to add that here. Right. Temperature rise equals end minus starting temperature. You'd want to work that out before you plot the graph, right? Precaution, because they have talked about safety precaution, right? Take care when removing beaker, use, let's say, gloves. Take care when removing beaker as it, one more line, contains hot water. So going back through the answer, use a measuring cylinder to add 100 ml of water to a beaker. Use a thermometer to measure the starting temperature. Then place the beaker in a microwave and switch on for 1 minute. Remove beaker from microwave and record the end temperature of water. Stir well. Temperature rise equals end minus the starting temperature. Then repeat for a range of times such as 1, 2, 3, 4 and 5 minutes. Then plot a graph to show the pattern. Take care when removing beaker. Use gloves as it contains hot water. Next question. Question number 4. Different wavelengths of light can be used to transmit information along optical fibers. Figure 3 below shows how the percentage of incident light transmitted through a fiber varies with the wavelength of light and the length of the fiber. So percentage of incident light transmitted. The dotted line is the 50-meter cable and the solid line is the 100-meter cable. Question 4.1. Compare the percentages of incident light transmitted through the two different fibers over the range of wavelength shown. So the range of wavelength shown is from 4 to 6.5 times 10 to the power minus 7 meters. That's the wavelength. Now what is actually happening over the range? For both, it goes down and then it increases. For both of them, it goes down at 5 times 10 to the power minus 7 meters. The reduction in the incident light transmitted on the 100-meter cable is much bigger than the 50-meter cable. So this is starting at 98 and that's 1, 2, 3, 4. So this is 86%. This is 96% and it drops down to 72%. So let's write the answer for this, because we are comparing for these 3 marks. Get down a little bit up. Okay, so first bullet point, right? For both 5 cables, for both fiber cables, increasing the wavelength of light decreases then increases the percentage or amount of light transmitted. second bullet point. Lowest percentage transmitted at 5 times 10 to the power minus 7 meters for both fibers or cables. Number 3, I could say the 50-meter cable transmits more light than the 100-meter cable. Question 4.2. The speed of light is 3 times 10 to the power 8 meters per second. Calculate the frequency of light that is absorbed the most by the 100 ml cable. So calculate the frequency. Remember the equation, wave speed equals frequency multiplied by the wavelength. So they have given you the speed. So rearranging this equation, frequency equals the wave speed divided by the wavelength. Wave speed is 3 times 10 to the power 8. And what would be the wavelength? Calculate the frequency of light that is absorbed the most by the 100 ml meter cables. So why is it absorbing the most? So according to the question, calculate the frequency that is absorbed the most. It will be absorbed the most is where it's transmitted the least. So the percentage of incident light transmitted the least is this wavelength of 5 times 10 to the power 7 minus 7 meters. So five times 10 to the power minus 7. So 3 times 10 to the power 8 divided by 5 times 10 to the power minus 7 equals 6 times 10 to the power 14 hertz. 6 times 10 to the power 14. Question 4.3. The inside of optical fibers consists of 2 layers of glass, core and cladding. Figure 4 shows how light travels between these 2 layers. So you've got cladding on both sides and the core. So as the light goes through the core, it's a straight line, and as it moves from the core into the cladding, it refracts at the boundary. Suggest why the light travels in this way in the optical fiber. Why is it actually changing direction here? They're not asking why is it traveling in a straight line, because light always travels straight line inside any given medium. Why is it actually refracting there? That's what the question is. So light refracts at the boundary between cladding, and 4. Why is this happening? Since light changes speed or slows down in cladding as it's denser than the core material. That brings us to the end of the paper. I will see you in the next video.